Assalamu alaikum dear students. Today we shall discuss the derivatives of the function in parametric form. Now what is parametric form? Now you know that in functions usually the functions are real valued functions, that is whose domain is set of real numbers and whose codomain is also the set of real numbers. In such functions we have two types of variables. One is called dependent variable and second one is called independent variable. Usually we consider x as independent variable while as we consider y as independent variable. Now here this x is related with y, means there is a relation between this x and y. Now if we are able to express this relation as y equals to f of x, means we are able to separate y and x to two sides. Such very type of function is simply called as explicit function. You know it, like y equals to sine x. Here x is separated, y is separated, means this is explicit function. Now if we are not able to separate x and y, then you know that such type of function is simply called as the implicit function. So we have two types of relations, which is simple. First one is explicit function and second one is implicit function. But there is another way to express the relation between this dependent and this independent variable. Now in this very situation we consider a third variable, say theta, which is simply called as the parameter. This parameter is related with x and with y separately but through explicitly, while as x is independent variable, y is dependent variable, which are related to each other as usual. Such form of function is called as parametric form of function. Like if we consider, let's assume that theta is the parameter, x is independent variable, y is dependent variable, such that here in this form, in parametric form, this theta is related with this x explicitly, while as this theta is also related with this y explicitly. Like if we consider x equals to f of theta, here this theta depends upon x, and this form is explicit form, while as this theta depends upon y through g, and this is the explicit form. This is called as the parametric form of a function. Here x equals to f of theta and y equals to g of theta, where theta is called as parameter of the given equation. Here this x equals to f of theta, this means x is related with this theta explicitly. Y equals to g of theta, this means that y is related with this theta explicitly, while as in turn x and y are related to each other as usual in functions. This means that this y is dependent variable and this x is independent variable. This very form of function is called as the parametric form of function. Like if we consider how to find its derivative, that is we have to find dy by dx, because this derivative means we have to find differentiate dependent variable with respect to independent variable. In this form, this x equals to f of theta, y equals to g of theta. Here in this x we differentiate with respect to theta, that is dx upon d theta equals to f dash of theta, because here theta is variable. Similarly in y we differentiate this with respect to theta, which implies that it is dy by d theta equals to g dash of theta, because here we are differentiating with respect to theta. Now we have to find dy by dx. Now dy by dx is dy by d theta into divided by dx by d theta. By cancelling d theta we simply get dy by dx, or this equals to dy by d theta into d theta by dx, because by cancelling d theta we simply get dy by dx. Hence this its derivative is dy by dx equals to dy by d theta into d theta by dx. We know dy by d theta and d theta by dx by taking the reciprocal of dx by d theta. Hence in this way we find the derivative or the differentiation. We do the differentiation for parametric functions. Now let me consider an example. If x equals to a cos theta, y equals to a sin theta, find dy by dx. Means here y is dependent variable, x is independent variable, theta is parameter. Now we differentiate in x as well as in this y. By differentiating with respect to this parameter, that is with respect to theta, dx by d theta is minus a sin theta, because here a is constant, and dy by d theta is a cos theta, because differentiation of this sign is cos. Now you know that dy by dx is dy by d theta into d theta by dx. Here dy by d theta is a cos theta. D theta by dx is, by taking the reciprocal of dx by d theta, is 1 upon minus a sin theta. This a cancels, we simply get minus cos theta upon sin theta. That is dy by dx is minus cot theta. So this is the derivative for this parametric function, where this theta is a parameter. Now here second example is x equals to 2at square, y equals to at raised to power 4. Here this a is constant, this t is parameter. So in place of theta we have here t. So let us differentiate this x and y with respect to t, because t is parameter. It is dx upon dt is 2a 2t, because differentiation of t square is 2t with respect to t, that is 4at, while as hence it is reciprocal, because in dy by dx we need the reciprocal of dx upon d theta or dt, that is dt by dx is 1 upon 4at, by taking the reciprocal of dx upon dt. Now similarly y equals to 84, by differentiating with respect to t we simply get dy by dt equals to 4at cube, because differentiation of t4 is 4t cube. Now dy by dx is dy by dt into dt by dx. Actually in above it was dy by d theta into d theta by dx, but here where this parameter is t, so replacing theta by t we simply get a dy by dt into dt by dx. Substituting the values we simply get 4at cube upon 1 upon 4at. 4a cancels, t and 1t cancels, we simply get t square. Hence its derivative is dy by dx equals to t square, where t is parameter, through x equals to at square and y equals to 84. Now if x equals to under root of a raised sin inverse t, y equals to under root of a cos inverse t, we have to show that dy by dx is minus y upon x, where t is the parameter, a is constant. Now here x equals to a sin inverse of t, which implies that this under root means it is actually the index, its index is actually 1 upon 2, that is a sin inverse of t raised power 1 upon 2, or simply by index laws it is a raised power 1 upon 2 sin inverse t, or simply a raised power sin inverse t upon 2, which implies that x equals to a sin inverse t upon 2. Similarly y equals to a cos inverse upon t by 2. Now taking logs, because it is the power function, here we have to find this dx upon dt, or we have to find dy by dt. We have power functions, which implies that taking logs by using the logarithmic differentiation. Log of x equals to log a sin inverse t upon 2, and log y equals to log a raised power cos inverse t by 2, which implies that log x equals to sin inverse t by 2 log a, and log y equals to cos inverse t by 2 into log a. By differentiating with respect to 2 in both equations, we simply get 1 upon x equals to dx by dt equals to, here this log a is constant, 2 is constant, so they comes out from this differential, while as differentiation of sin inverse t with respect to t is 1 upon t square. Similarly here this log a and 2 is constant, differentiation of cos inverse t with respect to t is minus 1 upon root of 1 minus t square. So which implies that dx by dt is x upon 2 log a by root of 1 minus t square, while as dy by dt is minus y log a upon 2 root 1 minus t square. But you know that dy by dx is dy by dt into dt by dx, which implies it is simply by substituting the values of dt by dx and dy by dt, we get minus y log a upon 2 root 1 minus t square into 2 root of 1 minus t square upon x log a. Now log a cancels, 2 cancels, under root of 1 minus t square cancels. We simply get dy by dx is minus y upon x, hence proved. So this means that when x is under root of a raised power sin inverse t into y equals to under root of a cos inverse t, then dy by dx is minus y upon x, because this is parametric, hence using the parametric differentiation. Inshallah tomorrow we will start new concept, that is second order derivatives or higher order derivatives. So thank you.